So we're now at the part where we want to discuss the properties of records that are recorded in a blockchain. And to do that, there's a few terms that I want to clarify and I want to describe what they are. So the first one I want to describe is hashing. So we want to know what is hashing and why do we use hashing? The definition mathematically is quite simple. You take a message that is any form of text, could be numbers, could be whatever you want to have. The hash of a message is essentially a fixed length output or digest of that message. So we describe the message as M, and H of M is the hash of the message. Why do we do this, and what are the important properties about this? Well, the first part, and it's really important, is it's deterministic, i.e., and that means it's not random. So if you take one message and you use a hashing function for it, it will always generate the same digest. Now, if you look at what a hash looks like, it looks like a randomly put together set of numbers and letters, but it is not random. It is entirely deterministic. It also has to be fast. So in order to create a hash, it has to be something that has to be really easy to do. So it's not something where you have an algorithm which runs for hours. It is unpredictable. So if you have two messages that are very similar, so if you take, for instance, my name, Andreas, and use it with a capital letter or without a capital letter, the digests that come from it will look very different, so that you cannot draw inferences from one on the other. It also has to be non-invertible, meaning that there is no inverse function, or rather, in technical term, there is no function there's no known inverse function, such that you can go from the hash to the original message in normal, i.e. polynomial time. It has to be an exponential time. Now, one thing that should be very clear is that the hashing algorithm that exists, there is no known inversion as an inverted function, but it may be possible that there is one. I don't think there's a proof that says it's not invertible. And it has to be collusion resistant. So it has to be very difficult for an attacker to find two messages that give you exactly the same hash in normal time. Now, one of the things that is to be kept in mind is that because the different hashes, every hash has a fixed length, there is a finite number, although a very, very large number of hashes that can be created. Whereas the input text, there's essentially an infinite number of them. And so this is important because it is possible that the same messages give you the same hash. It's just that it's not easy and sort of in the sense of in polynomial time possible to find two messages that are the same. Now, what is cryptographic hashing? Well, let's do a simple application. I'll talk about some applications. So for instance, databases should never store user passwords and usernames in plain text, right? Because, if you are an attacker and if you make your way into the database, then you would be immediately able to impersonate every single user. So normally a good database would go out and it would store information about users and their passwords in a hashed form. Okay. So if you store them as a hash, you can't really do the inversion. Now, some nerdy stuff here that you may be interested in is you may want to read out about P versus NP hard problems. So the idea is if a solution to a problem is easy to check, is it also that the problem itself is easy to solve? So, that's the difference between a P hard and NP hard problem. We don't know the answer yet. And if you manage to find the answer, then you can win $1 million or so in a math prize. Okay, so now what hashing functions exist? Well, there's actually many of them. There is one called MD5, there's SHA-1, there's SHA-256. Each of them is an improvement over the last. There is something called SHA-512. There is a RePMed 160, which gives you a particular type of output. Now, the SHA-256 is the one which is the most commonly used currently. It gives you a 256 bits output of any input text that you have. And just to understand the math here is 4 bits count for 1 character. So each of these hashes are 64 characters long. It was developed by the NSA, so National Security Agency, and the code is entirely public knowledge. Anybody can use it, and this is obviously a powerful tool about this, that everybody can use the same SHA algorithm to create the same output. There is no inconsistency and there's no disagreement about what the hash of a particular text will be. So let me give you an example. Here's the hashes of my name, Andreas. You have MD5, you have SHA-1, and you see SHA-256. You can see that the digests get longer as you go with more and more modern algorithms, hashing algorithms. Now, if you look at my name and you change a few of the letters from lowercase to capital letters, you can see how the hashes of these are fundamentally different. So there's no way how you can convert one for the other. And this holds for both the old-fashioned MD5, the SHA-1, and the SHA-256. They all are very different. Now, the question is, can these actually be hacked? And the answer is actually yes. So you can go to a website, go to CrackStation, and I try to crack my name, both of these names, versions of my name, one with the capital letters, one without them. So, and you can see how the MD5, the SHA-1, and the SHA-256 could very easily crack my name. Obviously, this is they just basically went by a dictionary. So they basically take all the words in the dictionary, possibly also in different languages, try them out, and if you find a match, then you know that you have just cracked the hash. But you can see that the SHA-256 could not crack my name with the capital letters. Why is that? Well, because the standard dictionary tag doesn't work for that. All right, so why are they used in blockchains? Number one, it is a very, very efficient way to represent data. So you take any length input that you have and you create always the same length output. So that's a very good convention in order to store information. Number two, if you have small changes to data, they trigger very large changes on a hash. So I showed you a demonstration in the last class. So the important part is that if there is any change in the data or in your database, it is very easy to check for consistency. Because you just need to look at the hashes, and if there's any small change in the database, you would be finding it to be very visible and easily seen. Yeah. And then finally, you can use them, or not finally, the third part is you can use them as pointers. So that means that, and this is the link in the block, the way we link them is each block contains a hash of the past block. So this is the link to the past block. Now you can, in a computer science sense, when you create data, if you can create data and use that in your memory, you need a pointer to that data. And a hash is a very easy pointer. That makes what that does, it makes actually searches through the database extremely easy. And then finally, if you have hashes of hashes, they are used to simplify data storage. And in fact, the Merkle root, essentially, the idea there is that it is a hash of hashes in a very particular format. And if you do hashes of hashes and do this repeatedly over and over for pieces of information, you create a Merkle tree, which again makes the search in a database extremely straightforward.